Hello everyone and welcome to my talk about improved hardness of approximation for distributed diameter. This is joint work with Ofer Grossman and Ami Paz. And I'm Seri. Okay, so let me start by explaining what is the diameter of a network. So given a network, the diameter is the maximum distance between any 2 points in it. For example, in California, we know that the 2 points that are farthest apart are Rockland and Bard. So the distance between these 2 points is what we call the diameter of the network of roads in California. The diameter is one of the most fundamental graph parameters. It plays a vital role in many theoretical computer science models. And in distributed computing, the diameter is even more fundamental because it captures the minimum number of rounds a message needs to traverse all the nodes in the network. And in this work, we're interested in diameter approximation in the distributed setting. So let's start. Okay, so the plan for today is as follows. First, I'm going to tell you about the distributed models that we work with. Then I'm going to tell you about some related work and compare them to our results. And our results are achieved via a well-known technique of reductions from the two-party communication complexity model. So then I'm going to tell you about this model. And then I'm going to show you the high-level idea of the proof of our main result. And finally, I'm going to conclude with some open questions. Okay, so let's start with distributed models. So the two main models of distributed graph algorithms are the local and congest models. In the local model, we have a network of n nodes and m edges. We have O of log n bit identifiers. We have synchronized communication rounds. And in each round, each node can send an unbounded size message to each of its neighbors. Okay? And we also assume that the nodes are computationally unbounded. And this is because we want to understand the pure challenges of communication. Okay, so we assume that at any node, any computation can be done for free. Okay, and the goal in the local model is to compute some function of the network while minimizing the number of communication rounds. So the complexity measure is the number of rounds. So that's the local model. And one thing that we know about the local model is that any problem can be solved in diameter number of rounds. And this is because we can simply gather the entire topology in D rounds because we have unbounded size messages. And then at any node, we can use unbounded computation power to solve any problem we want about the network. Okay, so any problem can be solved in D rounds in the local model, where D is the diameter of the network. What about the congest model? So the congest model is very similar to the local model, but the only difference is that the size of the messages is bounded by O of log n bits. Okay, so now each node cannot send an unbounded size message to each of its neighbors in each round, but they can send only O of log n bits in each round. Okay, and because we have this bandwidth limitation, we can't necessarily solve any problem that you want in the congest model in D rounds, okay, because we may have some congestion somewhere. But what we can show is that we can gather the entire topology in O of m rounds, even in the congest model, and therefore we can solve any problem that you want in O of m rounds, even in the congest model. Okay, so these are the two main models of distributed graph algorithms. And how fast can we compute the diameter in these models? So in the local model, we can solve any problem that you want in D rounds. And for diameter, we know that this is tight, even for approximations. And this is because we can show a standard indistinguishability argument to prove this lower bound. Okay? So for example, the nodes cannot distinguish between graphs of diameter D and graphs of diameter, say, 100D in less than D rounds. What about the congest model? So in the congest model, we know that in O of D rounds, we can find two approximation for the diameter. And this is because we can simply compute the BFS from some node U, and the depth of this BFS tree from the node U gives us a two approximation for the diameter of the network. And our main question in this work is, can we do anything better than that in O of D rounds in the congest model? Okay, so there is a folklore algorithm that gives two approximation in O of D rounds. Can we get anything better than two? And our main result is that even getting anything better than 11 over 6 already requires some polynomial dependency on n, even for constant diameter graphs. So we showed that there is a graph for which we can find the two approximation in O of 1 round, because this graph is going to have constant diameter. But finding anything better than 11 over 6 already requires some polynomial dependency on n. Okay, so this is our main result. And now let me tell you about some related work and compare them to our results. Okay, so if you want to find the exact diameter in the congest model, then we know that we can do it in O of n over log n rounds. And there is a matching lower bound. Okay, but if you want to settle for 3/2 approximation, then you can do it in O of root n log n rounds. But if you want to find anything better than 3/2 approximation, then we know that you will need near-linear number of rounds. And in this work, we show these new lower bounds. So we show a lower bound for 5/3 minus epsilon approximation, lower bound for 7/4 minus epsilon approximation, and our main result is a lower bound for 11/6 minus epsilon approximation. And we view this as our main result because the approximation factor gets very close to 2, for which we have a trivial upper bound of O of 3 rounds. Okay, so now let me tell you about the high-level idea of the technique that we use to prove these lower bounds. Okay, so we use a technique of reductions from the two-party communication complexity model. So in the two-party communication complexity model, we have two players, Alice and Bob. Each has an input string of size k. So Alice has an input string x, Bob has an input string y, and there is a communication channel between Alice and Bob. And the goal of Alice and Bob is to compute some function of their inputs while exchanging the minimum number of bits. Okay, and one of the most famous functions in this two-party communication complexity model is the well-known set disjointness function. And in this function, Alice and Bob want to know whether their strings intersect somewhere, so whether there is some index I for which xi is 1 and yi is 1, or whether their strings are disjoint, which means that for any index I, at least one of the bits must be 0. Okay, so this is the set disjointness function, and already in ICAT 1992, Razborov showed that Alice and Bob cannot solve set disjointness in less than omega of k bits. So they must exchange omega of k bits, which means that Alice and Bob cannot do anything better than sending their entire strings. Okay, and many works use this hardness result for set disjointness to prove hardness results for the CONGEST model. And examples include hardness results for MST and subgraph detection, distance computations, proof labeling schemes, distributed optimizations, and many more. And the high-level idea of such reductions is usually as follows. So Alice and Bob, before they start the protocol for set disjointness, they decide on a fixed graph construction G and the partition of G into G1 and G2, such that G1 is owned by Alice and G2 is owned by Bob. And I will explain what I mean by owned in a few seconds. Then, each of the players receives its input string. So Alice receives the string X, Bob receives the string Y. And each of the players adds some edges to their own graph based on the input strings. So we get G1X, we get G2Y, and the whole construction we call it GXY because now it depends on the input strings. And what we want to have is that the graph GXY has some property P, and think about P as being, for example, diameter equals 5, if and only if the sets X and Y are disjoint, or the strings X and Y are disjoint. So if we can have this if and only if, then Alice and Bob can solve set disjointness by checking whether GXY has the property P. And how can they check whether GXY has the property P? So assume that we have an algorithm in the CONGEST model that checks whether an input graph has a property P. Then Alice and Bob can simulate this algorithm on GXY as follows. Alice can simulate the nodes in G1X, and Bob can simulate the nodes in G2Y. And whenever there is a message from some node in G1X to some node in G2Y, then Alice sends this message to Bob. Okay? And whenever there is a message from G2Y to some node in G1X, then Bob sends this message to Alice. And because we have a lower bound on the number of bits that Alice and Bob must exchange in order to solve set disjointness, we get a lower bound on the number of bits that any algorithm must send on this cut. Okay, so any algorithm must send omega of k bits on this cut, because otherwise we will get a better protocol for set disjointness. And because we are in the CONGEST model, on each edge on the cut, we can send log n bits in each round, so we get a lower bound on the number of rounds, which is omega of k over the size of the cut times log n. So that's the high-level idea of this framework. And now let me show you an example of such a lower bound for a related problem called the ST diameter. Okay, so now I want to show you an example of a problem called ST diameter, for which if we can solve it efficiently in the CONGEST model, then Alice and Bob can solve set disjointness efficiently in the two-party communication complexity model. So in this problem, we have an input graph and two sets of nodes, S and T, and we want to find the maximum distance between some node in S to some node in T. So unlike in the diameter problem, in which we care about all pairs of nodes, here we care only about the pairs in S times T. Okay. So now I want to show you that there is a specific graph construction for which, if we can solve ST diameter on this construction efficiently, then Alice and Bob can simulate this algorithm to solve set disjointness efficiently in the two-party communication complexity model. Okay, so the fixed graph construction is as follows. We have 6 sets of nodes, S, A, B, C, D, and T, each of size root k. And think about k as just a parameter of the construction. For now, that equals 9. And the set S is connected to each of the sets A and B by a matching, and the set T is connected to each of the sets B and D by a matching. Okay, so we have 4 total matchings, each of size root k edges. So that's the fixed graph construction, and the partition of this graph into G1 and G2, the graphs of Alice and Bob, is as follows. The graph of Alice is the graph induced by the nodes S, A, B, and T, and the graph of Bob is the graph induced by the nodes in C union D. Okay, so this is the fixed graph construction. Now let me tell you which edges the players add based on their input strings. So Alice receives the string X and Bob receives the string Y, and each of the strings is of size K. And it's convenient to think about the positions of the strings as indexed by a pair of parameters ij in the set of numbers from 1 to root k. So in total we have k such possible pairs, so each pair corresponds to a specific position in the two strings. And if xij is 0, then we add an edge between ai and bj. And if yij is 0, then we add an edge between ci and dj. Okay, so for example, if x12 is 0, then we have an edge between a1 and b2. If x32 is 0, then we have an edge between a3 and b2. And if y21 is 0, then we have an edge between c2 and d1. So that's the construction. And now I want to show you that solving ST diameter on this construction implies a solution for set disjointness for x and y. And for this, I want to first show you that if the strings are disjoint, then the ST diameter of this construction is exactly 3. And I want to illustrate this by an example. So let's take for an example the pair of nodes S1 and T2. And I want to show you that the distance between S1 and T2 is 3. So because the sets are disjoint, we know that either x12 is 0 or y12 is 0. It could be that both of them are zeros, but we only need one of them to show that the distance between S1 and T2 is 3. So let's assume without loss of generality that x12 is 0. So we have an edge between A1 and B2. Okay? And because we have this edge, it implies that there is a path of length 3 between S1 and T2. Okay, and you can prove the same for any Si and Tj using a similar idea. What happens in the non-disjointness case? So in the non-disjointness case, we have at least one position in which the strings intersect. Okay, and let's assume without loss of generality that the position is 1, 2. So we have that x12 is 1 and y12 is 1, which means that we don't have any of these shortcut edges. Okay, and now what you can prove is that because we don't have any of these shortcut edges, one of them must be replaced by a path of length 3. Okay? And what you can show by some case analysis is that because at least one of them must be replaced by a path of length 3, the distance between S1 and T2 is at least 5. And you can show that in the non-disjointness case, the ST diameter of this construction is at least 5. And the key idea that we used here is that bipartite graphs have girth at least 4. So the girth of a graph is the length of the shortest cycle in it, and it's well known that bipartite graphs have girth at least 4. So here, because we had girth at least 4, we said that this shortcut edge must be replaced by a path of length at least 3. Okay, so we get a lower bound, and what is the lower bound that we get? So the size of the strings is k, the size of the cut is 2 root k, and the number of nodes is 6 root k, because we have 6 sets of nodes, each of size root k. So we get lower bound, which is the size of the string k over the size of the cut times log n, so root k times log n, which is omega of n over log n in this construction. And the key idea that we used again is that in the non-disjointness case, the ST diameter must be at least 5, because bipartite graphs have girth at least 4. right? Because we said that this shortcut edge must be replaced by a path of length at least 3, which implies that the distance between S1 and T2 must be at least 5 by some case analysis. And our main idea in this work is that if we used bipartite the graph of larger girth, then maybe we could get better gap than 3 versus 5. Because maybe in the non-disjointness case, if we had here a graph of girth larger than 4, we could have a diameter that is at least something larger than 5, which would imply that we have larger gap, which would give us an improved hardness of approximation. And that's exactly the idea of our full construction. So let me now show you our full construction. So in our full construction, we have again here two bipartite graphs, A, B, and C, D. But now we're going to make sure that these two bipartite graphs have large girth. And for this, we're going to use the following bipartite graph. So let H be an L by L bipartite graph with diameter D, girth 2D, and K edges. So in this example, L is 3, and we have an L by L bipartite graph with 6 edges, girth 6, and diameter 3. And that's because H in this example is just a 6 cycle. And in our construction, we're going to have two copies of H, Hx and Hy, where Hx depends on the string X and Hy depends on the string Y. And in Hx, we're going to keep only the edges that correspond to the 0 bits of X, and in Hy, we're going to keep only the edges that correspond to the 0 bits of Y. Okay, so the size of the strings is K, which is exactly the number of edges in H. And we're going to think about some arbitrary mapping between the set of edges of H to the K positions of the two strings. And if Xi is 0, then we keep the ith edge of H in Hx. And if Yi is 0, then we keep the ith edge of H in Hy. So for example, if X was the all 0 string, then Hx is just isomorphic to H, because we have all the edges of H in Hx. And if, for example, the first bit of X was 1, and it corresponds to this edge of H, then we don't keep the corresponding edge in Hx, so we don't have an edge between A1 and B1 in this case. Okay, and similarly, we keep in Hy only the edges that correspond to the 0 bits of Y. Okay, now let me tell you what are the cut edges between Hx and Hy. So we connect A and C by a matching, and we connect B and D by a matching. And observe that I wrote here the indexes in C and D in a reverse order compared to how I wrote them in A and B, just to make the cut edges clear visually. So we have A1 connected to C1, A2 connected to C2, A3 is connected to C3, and similarly between B and D. Okay, so now I'm going to show you some proof for the weighted case. So we're going to have some weighted edges, and then I'm going to explain how to extend it to unweighted graphs as well. And the only edges for which we're going to have weights are the cut edges. And the weight of the cut edges is going to be 0. So each edge on the cut has 0 weight. Okay, so that's the cut between Hx and Hy. Now I want to show you that if we can compute the diameter on this construction efficiently, then we can solve set disjointness efficiently. Okay, so let me start with the non-disjointness case. In the non-disjointness case, we know that there is some position for which the strings intersect. And let's assume without loss of generality that this position is the first position. So we have that x1 is 1 and y1 is 1. And in this case, we don't have an edge between A1 and B1, and we don't have an edge between C1 and D1, because the first position in the strings correspond to this edge of H, to the first edge. Okay, so what we can show in this case is that the distance between A1 and B1 is at least 2D minus 1. And unfortunately, I don't have time to go over the case analysis, but essentially all the cases are using the fact that the girth of H is 2D. Okay, so there are a few cases in which we can go from A1 to B1, and in all of them we can show that the length of this path is at least 2D minus 1 using the fact that the girth of H is 2D. What happens in the disjointness case? So in the disjointness case, we know that for any I, either xi is 0 or yi is 0. Which means that for any edge of H, it either exists in Hx or it exists in Hy. So this means that for any non-existing edge, there is a path that connects the two corresponding nodes of total weight 1. For example, if we don't have an edge between A1 and B1, this means that the first bit of x is 1, which means that the first bit of y must be 0, and therefore we have an edge between C1 and D1. And therefore, there is a path of total weight 1 between A1 and B1, even though they are not connected by an edge. And you can prove this for any non-existing edge in the graph construction. Okay? And using this, we can prove that the diameter of the construction is essentially the diameter of H. Okay? And because the diameter of H is D, we can prove that in the disjointness case, the diameter of our construction is D. So that's our construction. And I mentioned earlier that we have results for the unweighted case, and here we have some weights on the cut edges. So let's see how do we overcome these weights. So the first thing that one would try to do is to remove these zero weights from the cut edges. But before, when we had zero weights, it was useful because then using them doesn't influence the diameter that much. Now, when we have one weight on these cut edges, which means that the construction is unweighted, then using the cut edges might influence the diameter. And the way to get around this is as follows. So we stretch each edge in the graph, except the cut edges, by a path of length d. Okay? And when we do this, what we can prove is that the diameter is dominated by this path of length t, and the cut edges don't influence the diameter that much. And more formally, what we can show is the following. So we can prove that in the disjointness case, the diameter of the construction is t times d plus d. Recall that d is the stretch factor. And this additive factor of d is coming from using the cut edges. In the non-disjointness case, we can show that the diameter is at least t times 2d minus 1. So we get some gap here. And the quality of our lower bound in terms of running time depends on the density of H. So we want H to be as dense as possible. So for this, we use the existence of the following bipartite graphs, which were shown to exist by Benson and Singleton. So Benson and Singleton in 1964 showed that for d equals 3, 4, or 6, and for any L greater than 3, there is an L by L bipartite graph of diameter d, girth 2d, and a superlinear number of edges. So without going into the calculations, let me tell you what this gives us. When we set d 3, we get a lower bound for 5 over 3 minus epsilon approximation. When we set d4, we get a lower bound for 7 over 4 minus epsilon approximation. And when we set d6, we get a lower bound for 11 over 6 minus epsilon approximation, which is our main result. Okay, so that's all I wanted to show you today. Now let me conclude with some open questions. So the first question is naturally regarding 11 over 6 approximation. So in this work, we showed that any approximation better than 11 over 6 must have some polynomial dependency on n in terms of running time. Can we show that 11 over 6 can be achieved in O of d rounds or in anything better than our lower bound? The second question is regarding the hardness of the radius. So another important graph parameter is the radius of the network. And we are wondering whether the same hardness results apply also for computing the radius. And I'm just going to say that we believe that the answer is yes, but we couldn't prove it yet. The third question is regarding hardness of approximation for the diameter in the sequential setting. So the best conditional lower bound that we know for the sequential setting is for 5 over 3 minus epsilon approximation. And in this work, we get better hardness results for the CONGEST model. So the question is, can we somehow use our girth ideas to prove some better results in the sequential setting as well? So that's all I had for today. Thank you very much for listening, and see you in the online discussion.